You tap a piece of glass, and a video from a server on another continent instantly begins to play. We have come to expect this digital world to work effortlessly, as if it were magic. But peeling back the screen reveals a different reality. The global network is a chaotic, fragmented mess of millions of mismatched machines, diverse operating systems, and competing hardware manufacturers. This chaos only functions because of the application layer, a series of invisible, choreographed handshakes. These strict rules dictate exactly how information travels, preventing the entire system from collapsing into static. The fundamental unit of this rulebook is the client-server relationship. A server is simply a digital worker hosting software to provide a service, while the client is the device asking for it. This diagram shows how the client finds its target using a Uniform Resource Identifier, or URI. It acts as a precise digital GPS coordinate, combining the protocol, the host name, and the specific file path, so the request reaches the exact server intended. The internet relies on this rapid-fire dialogue between clients and servers. To avoid total data gridlock, every protocol in the application layer is designed for extreme specialization. The first job is finding the right address. Because computers speak in numbers rather than words, the Domain Name System, or DNS, acts as a global phone book. It translates human-readable domain names into the numerical IP addresses that routers use to move data across the network. Once the IP address is found, the server needs to know which specific job to perform. This is handled by network ports, designated doorways for different services. When you browse the web, your request aims for port 80. Here, the server uses HTTP to deliver the HTML code, the structural blueprints that tell your browser exactly how to format the text and images on your screen. Early web protocols were designed for academic sharing, prioritizing frictionless access over security. This meant that standard HTTP sent all data in unencrypted plaintext, where it could be easily intercepted and read by anyone on the network. As the internet commercialized, the industry moved to HTTPS on port 443. This update utilizes mathematical encryption keys to lock the traffic, ensuring that any intercepted data looks like unreadable gibberish. Transitioning to port 443 created the infrastructure of digital trust, providing the security required for modern banking and e-commerce to function globally. Web browsing is efficient for viewing content, but moving massive files requires a different approach. For heavy lifting, the network relies on the File Transfer Protocol, or FTP. To avoid bottlenecks, FTP uses a dual port system. Port 21 is the management speaker, shouting commands like upload or delete. Meanwhile, port 20 is the dedicated lane for moving actual data. This separation ensures the command lane remains clear during massive transfers. This same logic applies to how IT professionals manage servers from thousands of miles away. Virtual terminals have replaced physical keyboards, allowing administrators to access a distant server's command line over the network. While the legacy Telnet protocol transmitted administrative passwords in vulnerable plaintext, modern network professionals use SSH. This diagram illustrates how SSH fully encrypts the session, leaving threat actors with nothing but scrambled characters. Protocols like FTP and SSH demonstrate that the internet is an actively managed physical infrastructure, requiring specific tools for every specialized task. Direct human communication uses a similar division of labor. Email relies on SMTP as the outbound mail carrier, operating on port 25 to push messages from your device to the local mail server. On the receiving end, retrieval has evolved from the legacy POP3, which downloaded and deleted messages, to modern IMAP4. As shown here, IMAP4 synchronizes the data, allowing you to see the same messages across all your devices simultaneously. This shift toward real-time synchronization set the stage for the most demanding application of the internet, digital voice. Voice over IP, or VoIP, digitizes the continuous analog wave of human speech. It slices the sound into thousands of discrete digital packets that travel across the same data lines as our emails and web pages. The application layer treats human speech as it would any other file attachment. Your voice is simply data to be sorted, routed, and delivered to a specific destination. The network is a hyper-organized digital backstage. It relies on a hyper-specialized division of labor, where every protocol has a specific job and a designated port. DNS finds the address, HTTP delivers the page, SSH locks down the commands, and SMTP pushes the message. This specialization has reached the point where the conceptual boundary between making a telephone call and sending a computer file has effectively disappeared. Modern devices stream live audio data to IP addresses, relying on the same packet-by-packet delivery rules used to load a website or sync an inbox. Behind the glass, thousands of choreographed rules operate every second. This invisible symphony of engineering makes the illusion of digital magic possible. You're right in the middle of something crucial, a deadline at work, or maybe just streaming a movie, and suddenly everything stops. You are met with the dreaded, endless spinning wheel of a dead network connection. If you're like most people, panic sets in, and you immediately reach for the power cord on your router. It's the universal digital reboot, the tech equivalent of hitting a jammed vending machine and hoping whatever is stuck just falls out. But that approach relies entirely on blind hope. Modern operating systems intentionally hide the actual mechanics of your network behind a graphical user interface. A spinning wheel tells you a connection failed, but gives zero actionable data about why. To figure out what's really wrong, look past the shiny graphics and use a text-based interface built into your system, the command line. It acts like an interrogation room, bypassing the surface level to give you granular, layer-by-layer control over exactly how your machine communicates. By typing a few simple text commands, you replace random guessing with a process of elimination. You can systematically hunt down the exact point of failure by testing each layer of the connection, working strictly from the inside out. The very first step of our inside-out diagnostic starts at the core, your own computer. Before your machine can ever reach the outside world, it has to successfully establish its own identity on your local network. On Windows, typing ipconfig/all into the command line acts like a magnifying glass. It reveals your device's hidden network ID card, its IP address and default gateway, along with the exact time its dynamically assigned connection lease is set to expire. To get that lease, your computer executes the DORA process. It discovers a local server, the server offers an IP, your machine requests it, and the server acknowledges it. But if that fails, the command line shows a red flag, an IP starting with 169.254. Your computer panicked and self-assigned a useless internal address. When you see that dead-end address, you can try to force a network rebirth. Typing ipconfig/release tells your machine to formally drop its faulty configuration, and ipconfig/renew broadcasts a fresh request to the entire local network, asking for a new, valid identity. If your machine still can't pull a valid address after a manual renewal, you've narrowed the failure down to your immediate vicinity. The issue isn't a broad internet outage. It's a breakdown in the local handshake between your device and the router, likely caused by a hardware failure or a severed cable. Let's assume your local identity is completely healthy, and you have a valid IP address. The next diagnostic ring tests whether your machine can actually talk to the local router, your digital exit door. We use the ping command. Your computer fires a tiny data packet, an ICMP echo request, and waits for an echo reply back. Pinging your default gateway applies a strict logical test. If the pulse never returns, the breakdown is happening inside your own building. But if the gateway successfully replies, you expand the ring. You ping an external public address, like Google's 8.8.8.8, to verify your traffic survives the journey out into the wider internet. Getting a successful reply from an external server is a major milestone. It proves that your local network is fine, your modem is working, and traffic is freely flowing across your internet service provider's backbone. This brings up an incredibly common mystery. What if your computer can successfully ping that outside server, but typing a website address into your browser still gives you a dead page? Look closely at the bottom half of this terminal output. When you ping a name like www.cisco.com, the system first translates that human-friendly name into a numerical IP address, like 104.112.72.241. If pinging the number works, but pinging the name fails, your connection is perfectly healthy. Your network simply lost its connection to the domain name system, the invisible logistics directory that tells your traffic where to go. Sometimes, though, a ping just dies somewhere out in the ether, hundreds of miles away from your computer. For those cases, you need a utility that can reveal the entire path: Tracert. Tracert exploits a tiny piece of data attached to every packet, called the time to live, or TTL, hop counter. Every time a packet passes through a router, that counter decreases by 1. Tracert sends packets with low limits, forcing them to expire mid-journey. When a packet expires, network rules demand that the router that killed it must send a specific error message back to the source. By systematically increasing the counter and forcing consecutive errors, your machine precisely maps the internet, step by step, isolating the exact third-party routing hub that dropped your connection. Zoom out from your own computer, and you'll realize that millions of these invisible ICMP echoes, replies, and intentional TTL errors are constantly bouncing back and forth between servers across the globe right now, just to keep our entire digital infrastructure fully mapped and functioning. Yet, the modern computing experience is actively burying this raw diagnostic power. Hardware and software manufacturers continually hide these raw command line realities behind sleek, automated troubleshooting wizards and unhelpful loading bars. As devices become easier to use on the surface, they become much harder to actually understand. We are trading our collective technical literacy for convenience, losing touch with the infrastructure we rely on every single day. So the next time your connection drops and you're staring at a dead web page, resist the urge to just yank the power cord. Open your command prompt, send out a few digital scouts, and use your own deductive logic to track down the silence. You're right in the middle of a crucial point in a virtual meeting, and suddenly, everyone on your screen freezes in bizarre, distorted poses. Your audio drops completely, and the dreaded "connection unstable" message pops up. Your immediate reaction is probably to throw your hands up and yell, "The internet went down." But here is the reality. The internet itself did not break. You just lost your personal, localized connection to it. The global network is simply too massive and robust to collapse just because your home Wi-Fi dropped. To understand how this massive structure actually stays online, we have to look at how devices communicate. Every single laptop, smartphone, and smart TV gets a Media Access Control, or MAC address. This is a permanent physical identity hard-coded right into the device's hardware at the factory. A MAC address gives your device an absolute identity, but it provides zero information about its actual location. It is like mailing a letter with a person's name on the envelope, but no street address, city, or country. If we tried to build a global network using only these physical names, a device wouldn't know where to send its data. Instead, it would use a broadcast mechanism, which literally shouts to every other device on the network asking for a location. On a massive scale, millions of devices constantly screaming at each other creates a broadcast storm. That sheer volume of overlapping noise would instantly consume all available bandwidth, and the entire system would grind to a halt. To survive its own massive scale without self-destructing, the network absolutely requires a structured, multi-layered physical hierarchy. The first step in that hierarchy is the access layer. This is the localized entry point, essentially your personal digital driveway. It connects your end-user devices to the broader network through hardware like a basic switch or a wireless router. This diagram shows a local network setup where devices receive an Internet Protocol, or IP address. An IP address provides a logical location, grouping neighbors together. You can see computers H1 through H4 connected under a single switch, and H5 through H8 under another. By confining these devices to their specific neighborhoods, indicated by the network labels 192.168.200.0 and 192.168.1.0, the system isolates that local broadcast noise. This image illustrates the first major architectural requirement: scalability. Notice the highlighted cluster of new users on the far right. Because they operate on standardized rules, they can simply plug directly into the existing infrastructure. Because we handle growth at these localized, standardized access points, you can add hundreds of new users without degrading the speed for everyone who is already connected. Once your data packet rolls out of your local driveway, it hits the city streets. This brings us to the second tier of the hierarchy, the distribution layer. At this intersection, you find specialized hardware like routers and Layer 3 switches. They act as intelligent traffic cops, reading those logical IP addresses to control the flow of information between entirely separate digital neighborhoods. But even with smart routing, physical cables only have so much bandwidth. When everyone logs on at the exact same time, the simultaneous communication demands outpace what the wires can physically carry, creating severe network congestion. This graphic explains how network architects solve congestion using the second pillar of reliability, quality of service, or QoS. Look at the central router, actively sorting data into two distinct pathways. That router uses internal memory buffers, like digital waiting rooms, to prioritize specific traffic types. Notice the text boxes comparing these pathways. A live voice-over IP call requires priority to maintain a smooth connection. If those packets wait in the buffer, the audio drops. But standard web pages can receive a lower priority, easily tolerating a split-second delay. The network feels incredibly fast, not because bandwidth is infinite, but because routers are ruthlessly prioritizing time-sensitive data and intentionally holding back the rest during moments of heavy congestion. With priority established, your traffic clears the distribution intersections and flies onto the massive multi-lane interstate known as the core layer. This high-speed backbone spans the globe, exposing it to a chaotic physical reality. Cables are sliced by construction crews, data center power grids fail, and massive routers die without warning. To survive this constant physical destruction, networks use packet switching. Instead of sending a video file as one solid chunk, it is chopped up into thousands of independent, individually addressed pieces called packets. This diagram demonstrates our third pillar, fault tolerance. Look at the red crossed-out router at the top. When that device fails, the system doesn't crash. Instead, the surrounding hardware instantly calculates alternative physical detours in milliseconds, shown by the green and orange arrows. Because routing happens dynamically across redundant pathways, the end user is completely unaware anything broke. The network stays online by constantly outrunning localized hardware death. But all of that highly efficient routing means nothing if the data gets intercepted. This brings us to the fourth and final pillar, security. Administrators must protect both the packets zipping across the globe and the physical hardware processing them. This network layout shows security applied directly to the infrastructure. Notice the red blocked connection and the login prompt protecting the router. This upholds the CIA triad: confidentiality to encrypt data, integrity to reject tampered packets, and availability for authorized users. Yet, there is a very real vulnerability here. You can run the most complex software encryption in the world, but it is completely useless if someone simply walks right up to a core router with a sledgehammer. We often picture our data floating safely in an ethereal cloud, but the global internet ultimately survives only because its most critical physical hardware is literally locked behind concrete and steel. Let's go back to your desk. That frozen video call stutters for a fraction of a second, and then smoothly syncs back into real-time audio. In that tiny window of time, your voice data rolled down your local access driveway, was pushed to the front by distribution traffic cops, and rerouted itself around a dead piece of hardware somewhere on the core interstate. So the next time you see a loading wheel, remember what is actually happening. You're watching a massive, fault-tolerant engineering marvel working relentlessly in the background just to deliver a tiny piece of the world to your screen. Before virtualization, corporate server rooms were physical bottlenecks. Network infrastructure relied entirely on discrete towers and servers stacked in dense metal racks. Systems administrators operated under a rigid one-to-one architecture rule: one motherboard, one job. If a network required a DNS server, an email server, and an SQL database, IT procured 3 separate hardware units. Sharing a machine risked severe operating system dependency hell. A single memory leak in a web server could crash every service on the box. This schematic details the typical layout of that era, assigning discrete boxes for web, email, and SQL. By strictly isolating software to distinct hardware, data centers generated massive operational waste. The average dedicated CPU rarely exceeded 15% capacity, yet the box drew full electrical power and required constant physical cooling 24 hours a day. This sprawl compounded physical risk. Multiplying the number of distinct physical hardware instances in a room linearly multiplies the exact number of single points of failure. 20 dedicated servers mean 20 power supplies and 20 motherboards that could suddenly short out. Hardware vendors initially treated the physical symptoms. They pushed redundant power supplies and expensive ECC memory, trying to make the individual boxes more resilient without addressing the core utilization problem. Scaling beyond these constraints required a structural solution for operating systems to share physical resources safely. Traditional operating system kernels like Windows and Linux are strictly selfish architectures. They are coded to expect total, undivided control over the physical hardware they boot on. We see the security hierarchy in x86 privilege rings, the architecture governing silicon-level hardware access. OS kernels are programmed to sit securely inside Ring 0, required to send direct instructions to the physical processor. Booting multiple kernels on the exact same CPU breaks this architecture. They fight for control of Ring 0, resulting in an immediate system halt. Early software-based workarounds attempted to intercept and translate these conflicting commands. However, binary translation at the software level introduced significant computational overhead and latency. To achieve true multi-tenancy, engineers had to move beyond software patches. They had to structurally re-engineer the privilege architecture of the physical processor itself. Silicon manufacturers like Intel and AMD bypassed the binary translation bottleneck by altering physical processor designs. They baked hardware-assisted virtualization directly into the physical architecture of the chip itself. This modification created a new privilege level beneath the OS, Ring -1. Here sits the hypervisor, a critical abstraction layer. Its sole function is to schedule CPU instructions and isolate memory spaces, keeping the guest operating systems above completely unaware they share hardware. This hardware-assisted abstraction is the mathematical mechanism that makes highly efficient, scalable virtual machines possible. In practice, the industry splits this hypervisor architecture into two distinct operational deployments. This diagram maps the Type 1 or bare metal approach. Here, absolutely no host operating system acts as a middleman. The hypervisor is installed directly onto the storage controller. This grants the hypervisor heavy-duty, uncontested hardware access. Hyperscale data centers rely on this to run physical servers securely at massive utilization rates. Contrast that with the Type 2 hosted approach shown here, commonly used by developers for local desktop testing. An operating system layer acts as an operational barrier between the hypervisor and the underlying hardware. This extra layer creates an inherent latency penalty. When a virtual machine writes data to a disk, it passes instructions through the hypervisor, then through the host kernel, before finally reaching the physical storage controller. While hosted environments offer convenience for local testing, the modern data center relies on bare metal deployment to reach utilization levels of 90%. Because the bare metal hypervisor handles the hardware allocations, a server is reduced to a simple text configuration profile and a virtual disk file. Converting physical states to fluid data enables live migration. Administrators can move an actively running server across physical motherboards without dropping a single network connection. The hypervisor copies the configuration profile and active RAM from server A to B. Because server A is still processing live transactions, its memory changes. The hypervisor tracks these modified deltas, rapidly copying them in a continuous shrinking loop until the mathematical difference becomes microscopic. For a fraction of a single millisecond, the hypervisor freezes CPU execution on server A to push that final memory delta across the wire. It instantly broadcasts a new ARP packet, forcing the physical network switches to recognize the virtual machine's new physical port location. Server B immediately unpauses the CPU. The active TCP connection remains intact, leaving the end user unaware that the underlying hardware was just swapped beneath them. This same abstraction allows for physical to virtual conversions. Legacy critical infrastructure, previously locked to decaying motherboards, can be wrapped in a virtual disk and booted on modern silicon using generic drivers. By treating rigid hardware states as fluid data files, virtualization allows administrators to shift workloads across clusters, creating a path for fault tolerance that was impossible with discrete hardware. When data centers mastered bare metal hypervisors and live migration across thousands of machines, they forged highly elastic pools of global computational resources. Cloud computing provides the commercial framework for leasing these hypervisor-managed resource pools over the internet. Providers lease access based on abstraction depth. Infrastructure as a service grants access to raw virtual machines and storage. It offers maximum engineering flexibility, but requires the highest administrative burden to maintain. Platform as a service abstracts the underlying operating system and middleware completely. Developers deploy their code directly onto the framework without managing kernels or configuring database engines. Software as a service completely manages the stack. The provider handles everything from the bare metal hardware all the way up to the user browser interface. Deployment models dictate the physical isolation of these services. Public clouds rely on multi-tenancy, dividing shared silicon among many users. Private clouds guarantee dedicated, physically isolated bare metal to satisfy strict regulatory compliance. Organizations often link these environments using a hybrid cloud architecture. A secure private database can safely bridge its data to elastic public servers to handle sudden spikes in web traffic. This hybrid bridging relies on software-defined networking, using encrypted IPsec tunnels and virtual private clouds to keep the environments strictly separated. From public to private, the cloud is defined by how deeply the hypervisor masks physical reality from the end user. The continued expansion of these hyperscale data centers raises questions about the long-term role of local hardware. If a remote hypervisor can reliably deliver applications across the globe, the necessity for powerful local processing may shift. As network latency continues to drop, the requirement for complex, heavy local operating systems may decrease. This trajectory suggests a potential future where personal devices function as thin clients, glass screens acting as portals to remote virtual machines. Virtualization continues to distance the user from the physical silicon, replacing the local computer with a layer of remote, hardware-assisted abstraction. Looking at this standard network topology, you will immediately recognize the address assigned to this endpoint, 192.168.10.10. This classic dotted decimal IPv4 format acts as a clean digital dashboard built entirely for human administrators. We rely on this base 10 numbering system because we naturally count in tens. Grouping these digits into 4 distinct sections separated by dots makes intuitive sense, mimicking the structure of a familiar phone number. But the hardware actually routing your data possesses no human biology. Underneath that metallic casing, the router has absolutely zero concept of the number 192, and it does not comprehend the base 10 system. That familiar user interface is a complete disguise. If we view the exact same network topology as the hardware sees it, the addresses are exposed as massive, continuous binary strings. The machines are communicating back and forth through a relentless, unbroken torrent of raw electrical pulses, transferring data at lightning speed. When a local network is healthy, relying on this user-friendly illusion is perfectly fine. Automated calculators and software layers effortlessly handle the translation between our human decimals and the machine's code. But when data packets begin dropping into a black hole, you are dealing with communication errors at the absolute lowest hardware level. To borrow an aviation analogy, you don't need to know the chemistry of jet fuel to fly the plane, but you must know the route of the fuel lines to bypass an engine failure. Hardware makes routing decisions by running raw electrical pulses through an algorithmic filter called a subnet mask. It mathematically determines whether a packet travels to the server room down the hall or across an undersea cable to Tokyo, based on the state of those individual bits. When this mechanical logic fails, high-level automated tools cannot see the breakdown. A network administrator must strip away the decimal disguise and manually analyze the binary traffic to see how the silicon is misdirecting the data. To understand how silicon processes data, we must look at a modern microprocessor's physical environment. This dense architecture houses billions of microscopic transistors. These transistors face a rigid physical limitation. Like microscopic light switches, they physically snap closed to hold an electrical voltage or open to hold nothing. This mechanical reality maps directly to the base 2 binary system. An active charge represents a 1, and an empty wire represents a 0. We refer to each individual physical state, a single 0 or a single 1, as a bit. There's no physical margin for ambiguity in an electrical pulse. The transistor's binary physics create the inescapable foundation for every human-built networking standard. Translating decimals to physical voltages uses the 8-bit positional value table, mapping powers of 2, 128 down to 1. Each slot turns on once, or stays off, steadily subtracting from our target. Let's translate the start of our IP, 192. We start at the largest value on the left and ask, is our target, 192, greater than or equal to 128? It is. The switch flips to 1. We subtract 128, carrying the remaining 64 over to the next position. Next, we ask if our new remainder of 64 is greater than or equal to the next slot's value, also 64. Being an exact match, the switch flips to 1. We subtract 64, and our remainder instantly drops to 0. Because the remainder is completely exhausted, the remaining 6 slots automatically stay turned off. We fill them with zeros. We've just proven that 192 perfectly translates to the machine instruction of 2 ones followed by 6 zeros. When the foundations of the internet were designed, this 32-bit architecture yielded roughly 4.3 billion unique IP addresses. During an era where computing meant a single massive mainframe isolated in a university basement, 4.3 billion felt inexhaustible. Then, the Internet of Things arrived. Suddenly, we transitioned from one desktop per household to billions of smart refrigerators, connected thermostats, autonomous vehicles, and smartphones coming online simultaneously. Every single one of those endpoints requires a distinct IP address to route data. That massive influx of global hardware quickly drained the 4.3 billion address pool dry. The 32-bit system hit a hard physical bottleneck, breaking the internet's ability to scale. This hardware shortage necessitated the deployment of IPv6. This format expanded addresses to 128 bits, generating enough combinations to assign an IP address to every single atom on the Earth. But this massive expansion created an immediate logistical flaw. Asking a human network engineer to accurately read, write, or type 128 consecutive ones and zeros into a server terminal guarantees catastrophic typos and system crashes. The industry needed a powerful new visual disguise to compress these unwieldy addresses. The solution was the base 16 numbering system, better known as hexadecimal. We couldn't just use our familiar base 10 numbers to shorten the string. Because 10 is not a power of 2, it does not divide cleanly into binary memory. Forcing base 10 onto a binary stream leaves jagged, uneven data fragments that processors struggle to parse efficiently. Base 16, however, is mathematically flawless for compression. 16 is exactly 2 to the 4th power. That means all 16 possible states of a binary sequence fit precisely into a tidy 4-bit chunk, filling the space perfectly without a single wasted fraction. By utilizing the numbers 0 through 9, and then borrowing the letters A through F for the higher values, hexadecimal acts as the ultimate shorthand. One single alphanumeric character seamlessly represents 4 raw binary bits of data. Our numbering systems are completely beholden to the physical constraints of the hardware beneath them. As we stand on the edge of the next leap in design, shifting to quantum computers where bits can exist in multiple states simultaneously, we may be forced to invent new mathematical languages simply to read the dashboard.